everyone. Welcome to week 6, climatology. We are wrapping up our last week of talking about really the chemistry, the science, the physics, all behind climatology. And then we'll be moving into talking about how then we model this and in the adaptation stage and everything next week. So so this week I'm really going to focus in on I think what I consider the key points. If you've read the chapter, hopefully you have, you realize there's an awful lot of physics behind this, and this is why actually most atmospheric sciences programs are based largely in physics departments. I mean, it's almost like the new version of physics, or it's certainly the abundance of where I know the most physicists is in the atmospheric sciences. And I think this chapter demonstrates pretty clearly why. Right, there's an awful lot going on here, and so I will do my best to just focus in on the essential pieces, and we'll go from there. First, our fun fact for the day. This is another map from my buddy Brian, and he produced this actually a couple of years ago, and I'm still looking for another one that's very appropriate. But as you know, we're talking about the sun angle, and we're talking about the exposure of Earth's surface at different sun angles. And he's created this map talking about hours of daylight on the winter solstice. And this obviously just shows North America. Right? It would be a very different story for South America, but it's pretty fascinating, right? Like it follows these pretty direct lines of latitude, um, and it's fun. I mean, I don't know if how many have gone sort of latitudinal directions in their living, but certainly I have, and so I've experienced all the way up here, where there's really only about 5 hours of sunlight in the dead of winter. The rest is dark, 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 all the way down to here, where the least amount of sunlight we ever have is 9 to 9.5 hours, which is pretty cool. But even my folks who live up north of Seattle are a solid hour less of sunlight than what we get. So hopefully you guys have experienced that at some point. But it's always fun to think about this. Okay, so we're talking about atmospheric circulation. I'm going to cover atmospheric circulation, a little bit of the hydrologic cycle this lecture, and then we'll pick up on more of the hydrology, but especially the oceanic circulation that are all really key parts of what we observe in our climate. So this should look pretty familiar, both from the book, but also from our exercises a week and a half ago, 2 weeks ago. Back in week 4, when you were playing with those simulators, right, at the Earth 1 and Earth 2, and figuring out sort of the rates of solar insolation, and how that varied, assuming various concentrations of greenhouse gas. Even with all of our understanding of carbon cycle now and the greenhouse gases, it's very obvious still that solar insolation plays a tremendous role, right, in the both the heat and the temperatures that we see, but also therefore the precipitation and the amount of moisture in the atmosphere. So you kind of know temperatures range from -40 to positive 30 degrees centigrade in the tropics. -40 centigrade is actually pretty close to -40 Fahrenheit. It does even out there. Positive 30 centigrade is like 90s in Fahrenheit. Just in case you're totally not into the metric system. Cool. So when we start thinking about the role of solar insolation, we remember the greenhouse kind of experiments you're doing with the Earth 1 and Earth 2. Remember that sort of just the incoming solar radiation would look something like this. The right here, right, the absorbed solar radiation would look something like this. It's primarily focused in on the equator. That's the maximum sun angle, right? Something like this, incoming sunlight. And then it degrades significantly as you move up or down in latitude. Latitude matters, right? But we know that there's this emitted thermal radiation that plays, or terrestrial, not thermal, but emitted terrestrial radiation that plays a significant role in buffering that. And that's due to land masses, that's due to vegetation, and due to water, as you know now. So the real difference is that when we look at this and we're thinking about the role of atmospheric circulation in the solar insolation, is focusing in on the net gains and the net losses. So anytime these things cross, right? So this is the absorbed solar radiation, coming from the sun, right? If it's greater in watts per meter squared than the emitted, that means there's a net gain of energy up here. And in regions where the emitted is greater than the absorbed, that's a net loss area, right? And so this is really important because we're absorbing energy up here in the mid latitudes, right, up to about 40 degrees north and south, and then everything beyond that, we are emitting more energy than we're absorbing from the sun. So where does that energy come from? Well, this, right? Um, it's basic physics. Well, it's not so basic, to be honest. It's really complicated physics, but heat always wants to go to a cooler place. So energy always wants to become more stable, and heat is a less stable form of energy. So it always wants to cool down. And so when you think about the amount of absorbed radiation happening then at the mid latitudes and the equator, it's naturally going to want to move into those higher latitudes. And so this is what this graph is showing. You see this strong south uh, movement or pull of energy. This is the flux of energy, right? This is from the book as well. Um, and down towards the southern the south pole, and then here a high flux towards the north pole as well. And it's right at that convergence, right, is the maximum, and that makes good sense because that's where these two things meet. But still, just the fact that there's an awful lot of flux happening up in the upper latitudes is really key. So that means most of the energy is hitting here, but it's actually being pulled up here by basic laws of thermodynamics. This plays out really, really strongly then in the way that we see energy and therefore air and therefore like heat and precipitation moving across the Earth's surface. So we know that that both pressure and temperature vary with altitude. And so what we have here is right. You have all the heat coming in the Earth hitting us here. It's heating up so much that it rises up. It's trying to get cool, right? So it rises up, creates these convection clouds that are really high above the equator. And then that says, we got to cool down. So it starts moving towards the poles. And it moves and moves and moves. And some of it drops off here, right at the tropics, Tropic of Cancer up here and Capricorn down here. Some of it goes all the way up to the pole and then circles back down. And as it circles back down, and so when it gets up here, it cools down, right? It's lost all of its moisture holding capability. We'll talk about that in a second. It moves back down, then it gets kind of sucked in through convection back into the equator. So it's both kind of acting as a vacuum for the cold air, but also as a blower to push the cold air or the warm air up and out. And the reason it cools down is because of this, the lapse rates. There's a couple of different lapse rates. There's the dry lapse rate, there's the wet or moist lapse rate. There's the and then there's the earth, or the, I guess it's called environmental lapse rate on this slide. That's the lapse rate that we observe every time we go up a mountain. So we all know that if you go up into mountains here, it cools down. It's a similar concept, but it's different physics, right? So the environmental lapse rate is more based on the actual radiation hitting the Earth, and then the air cooling as you go up. The other lapse rates, the wet and dry, or the moist and dry lapse rates, are actually more based on physics and that pressure. So not necessarily the radiation, it's the pressure that exists in the upper atmosphere versus the lower atmosphere. But you still absolutely get that cooling effect as you move up, because air up here is a lot less dense. So go back to, to this, right? So pressure increases as you move into the troposphere significantly. Stratosphere, mesosphere, thermosphere, all that. It's really, really, really low pressure, meaning the air has plenty of space to spread out. That cools it, right? And it's not until you really compress it that it starts to warm up. You get those air molecules bouncing off of each other and creating all that heat. And that's simply because of this pressure here. So you have the different adiabatic lapse rates. You have the wet up here that's in the cooler air kind of status. And so that's a little less sharp, right? So the cooling is a little less pronounced. The dry adiabatic lapse rate, which is here, is a little bit more significant. And then the environmental is sort of this average of the both functionally. But again, it's a very different thing. But that's what we observe, when we just hike up a mountain. So all this comes together to create this figure from the book, right? So we've got the physics of air movement happening because of the solar radiation hitting the equator the strongest, and then degrading as you move up in latitude. This creates the convection pressure that pushes hot air up and over as it cools down because of that pressure, lack of pressure. It starts to sink, and then it starts, because it kind of gets sucked in, and then it starts to warm up again and move back down to the equator. Same up here. When it starts to warm up here, sometimes you get this upward movement because we've got the polar high, we've got the polar vortex that sits up here, largely formed by ice. And I put a video of this on Moodle, so hopefully you can watch that video on this. And this exists up here, so it kind of pulls some of that hot air up, and then it cools down and it circles back down and starts this cycle back over again. It's all broken up by the tropics, right? And hopefully you have had some exposure to this, like in ES 101. But remember, the tropics and these breakup of the cells are largely due from the Coriolis effect. That's the Earth's rotation, right? And because of that rotation, and I've posted a video from NOVA as well on Moodle for this as well, because I just love the physics explanation of these things in simple terms. And I can still picture my physics instructor doing this experiment. And he was like 75 years old, and he would take a nap right before our class. So he would always come in with hair smashed up against on one side. He was pretty awesome though, because he'd sit there and he'd spin around on like the little bar stools, the bench stools for in science classes and labs and whatnot. And he would do this centrifugal experiment with us, and just seeing a 75-year-old with smashed nap hair doing this. That's always what I imagine when I think about this. But so you've got that force happening, which creates these different latitudinal breaks in the circulations. So we've got physics operating from the rotation of the Earth. You've got physics operating from the massive amount of energy hitting the Earth's equator, and then physics caused by the pressure, and what happens to the energy as you move up and down in pressure. So all these are combining, right, to create these really interesting trade winds and subtropics that have all kinds of ramifications for both temperature and precipitation, right? Because these winds have a big impact on humidity. So you can see all these trade winds coming up into these equatorial lows, which then provides all this water off the ocean to accumulate here where all the radiation is happening. This is why we get those really high cumulus clouds, or Coriolis clouds up in the upper atmosphere in the tropics. They cool down as you get out here. This is why we have the westerlies here. We've got a little bit of change in pressure here, which is pushing the winds this way. The precipitation's coming off the ocean here. It's coming on, and it hits all the coastal ranges, and then it goes on and eventually picks up more moisture out here in the plains, and floods out the East Coast regularly, it seems, these days. And so all these determine like the jet stream and everything, although I'm going to hold off and talk about the jet stream a ton until we talk about the ocean circulation, because that's a big part of it. But yeah, hopefully watch the thing on the polar vortex as well as the Coriolis effect, because both those help really kind of explain the polar vortex is great because it's specifically targeted towards, understanding, this kind of diagram. So that's really the key, right? It's just to realize that we've got these different forces operating at different latitudes. And it's like 3 levels of physics all happening kind of simultaneously. And it's fascinating when we start talking about the models. All of this movement, I mean, they literally build layers of the model to capture this transfer of energy as it moves up and down in pressure. And you can imagine it has to be layers segmented by these subtropical, the lines of the tropics of Cancer and Capricorn. It's amazing. And then the 60°, because they have to capture the polar vortex and the Antarctic. I think the Antarctic has something similar, but it's not nearly as pronounced as the polar vortex or the polar eye. So yeah, you can imagine just how complicated these models start to get. But obviously, this has a big impact on both the temperature we see, but also the potential for precipitation. And this is why the book kind of showed this, right? We know all this happens because we literally see it in the vegetation. This is from NDVI, the Normalized Difference Vegetation Index composite, and it very clearly shows that the role of the equator and those subtropics, in precipitation, because we see it in the vegetation and we see it in the precipitation measurements. This is really cool. I actually wasn't fully aware of this satellite product before, but I knew satellites were being used to measure precipitation, because we don't have like rain gauges out in the ocean, which makes it really, really complicated to understand the flux of water as it moves from the ocean into the atmosphere. But what we do have is satellites taking pictures out there. We do have a lot of rain gauges now that kind of censor it. But boy, back in the 70s and 80s, luckily we had some satellites that could pick up some of that. And so this shows just that precipitation effect that's caused by the Hadley cell, the subtropics, and then that redisposition of heated energy, or energy kind of coming off its heat and storing water and then dumping that back up and then cooling down before it hits the poles. Pretty neat, huh? So yeah, this merges both terrestrial and satellite imagery, not imagery, but satellite readings to give an estimate of precipitation on average per day in millimeters. Pretty neat, huh? Okay, so this gets us squarely into the hydrologic cycle. And I don't know how many have already taken hydrology, but certainly you're going to spend, if you haven't, you're going to take it next term, because it's typically offered in the spring, and you're going to spend an awful lot of time with this. So I'm not going to spend a ton of time, but obviously hydrology has a huge role in understanding climate and these cycles. And it's just like the carbon cycle. We have to remember that it's there's not really a starting point or an ending point. It's literally this constantly moving, constantly fluxing system where, of course you have the oceans, which is the bulk of our water, right? But then you have all the forms that it exists in the terrestrial landscape, both in ice and snow and permafrost, which is like 2% of the Earth's water. If the ocean's like 70%, I think this is like 2 or 3%. A ton of it is groundwater. I can't remember actually the proportions these days. And then a very, very little amount is, sitting on the surface as freshwater lakes and rivers. But then you have all the mechanisms that allow them to either come out of the atmosphere or go back up into the atmosphere, go into the ground, which then sometimes gets up through the atmosphere via like respiration of plants, or transpiration of plants, sorry. It's remarkable, right? There's awful lot going on. It's been driven by the energy cycles and all kinds of other things. So why is it being driven by the sun? Well, because we understand this whole latent heat concept, this well, or heat capacity kind of concept. So um, hydrologic, or I mean the biggest bridge between hydrologic cycle and atmospheric cycles is just this relationship of energy and water, and the fact that water has these three dominant phases, um, all determined by the amount of energy stored within that water. You can kind of see where this starts to make a difference. If we know that 2 or 3% of our water is locked up in this ice, um, glaciers and that sort of thing, it's really important to kind of understand how much energy it takes to convert, um, ice, which is here. So it's from -30. We need to add about 63 joules to warm it up to even start to melt. And then once it starts melting at 0 degrees centigrade, right, 32 degrees Fahrenheit, it actually takes a decent amount of water or energy just to completely melt the ice into full liquid form. So you have the initial energy that it takes to start the melting, and then you have to kind of sustain to keep it melting, and that's about 330 joules to continue the melt. And it's important to realize that temperature, the ice or the water temperature doesn't change in that time period, even though it's absorbing more energy and it's converting the phases from ice into water. It's not changing the temperature. That's the heat capacity of water right there. um, and But then, boy, as soon as you start boiling it, I mean, it takes a tremendous amount of energy to get it to the point where it boils. So you've got the water here, you're now in the full water, and that's a lot. I can't remember the exact number from the book, but it was an awful lot. It depends too on how much pressure you have. I don't know if anybody's lived at higher altitudes, but it takes a good bit longer to get that water boiling, um, and a good bit more energy to get that water boiling when you're in higher elevations, and that's because there's less atmospheric pressure, right? So less atmospheric pressure means that there's less, it's less confined, right? The water molecules are less confined in that physical space, and so it's easier for it to dissipate the heat. So it takes a lot of energy and effort to boil that water. Um, so, but once you get it boiling, now to fully vaporize it. So, I mean, think about this. We're talking about like this much ice and water. To fully vaporize it, it's up here. It's, I mean, 5 times this amount of water or of energy, to completely vaporize the water as it does to get it boiling. And this is significant because all the water transfer from Earth to atmosphere is vaporized, right? So this is why we have so much heat holding capacity in water. It's remarkable amount of energy before we vaporize it. And that's how much is being absorbed. That's how much energy is going into that water being then transferred up into the upper parts of the atmosphere. And that's how much heat is released when it gets up there and it cools down. This is why water vapor is one of the most important greenhouse gases, right? It holds it there, and it once it releases, man, it's a big amount of energy coming out. And so I figured I'd just show you real quickly, the book attempted to do this connection between both hydrologic and the atmospheric cycles. So if you're looking at the intertropical convergence zone, right, um, and that's where all the energy is coming in, right, and you look at the 30, you assume that there's a temperature of 30 degrees centigrade. You can calculate how much water there is, how much grams of water vapor it has by simply doing this, right? Looking at 30 degrees C, drawing that line across, and it's about 27. I think he rounded up the other to 30 when he kind of talks about it later, but that's 27. So when it cools, when it air ascends to the top of the troposphere and it cools at about -30, well, that's down there. It's off the chart, right? So that means how much water vapor is lost? Well, all of it, literally all of it. 27 grams, it's gone. And so then it needs to, and it kind of gets sucked down, and it starts to get warmed up. But it doesn't have any moisture, right? So it's going to suck all the moisture out of the atmosphere, all the moisture out of the flux. And this is why you get that drying in the subtropics. This is why all the deserts line up with tropics of Cancer and Capricorn. So you have this just tremendous loss of humidity there. It finally regains it, and then it starts the whole cycle again. This is important when we're thinking about the movement of this water up and down in the atmosphere, and the whole concept of condensation. So hopefully you guys clicked on this video and kind of illustrated how condensation works. It's pretty awesome, right? It needs that nuclei to be there, and this is where those aerosols become important in the atmosphere as well. This is also, I don't know if folks have heard or read about cloud seeding. It seems like it's not a popular option these days anymore, but it sure was a big deal in the 90s and 2000s. It was, I mean, they cloud seeded all over Nevada to try to increase the amount of precipitation falling, especially as we started to see less and less fall. They're trying to mitigate it with putting these clouds, these nuclei up into the atmosphere, and I believe it was silver ions. I can't remember exactly what it was that they're using as a nucleus, but basically that was their solution, right? Like, well, we can't get enough precipitation, so let's go ahead and see if we can jumpstart it and give the atmosphere some nuclei that can then start to hold this water vapor long enough so that it can condense and give us these clouds. And so, yeah, this is really important because this condensation typically occurs when the air is cooled, i.e. when it's moving up in the layers of the atmosphere. So most often this happens right with mountains because it actually literally pushes the air up in elevation. And this latent heat releases during condensation, clouds lead to warming, and thus more, intense upward movement. So yeah, obviously a little bit more physics happening here with that condensation kind of piece. And this is where those really massive clouds come from in the tropics. This is how we're able to so easily move moisture around and heat, right? So this gets back to the heat holding capacity of water. And I really like these figures, both, I believe both from the book, right? And just showing the amount of energy that is stored in the ocean versus the atmosphere versus land. And you all saw this, right? You all saw how much the effects of water has had on both our observations, right? So thinking back all the way to week 1 and 2 when we were looking at the observations and seeing how global ocean temperature hasn't risen at the same rate as global land temperature. This touches on what we saw a couple weeks ago with Earth 1 and Earth 2 and the maps of the buffer effect. And it just matches what most of us know, especially living relatively close to the Oregon coast. We drive over there in the middle of winter now, right? Because it's so much warmer because you have the ocean sitting there buffering. And the ocean has 1,000 times more heat holding capacity than the atmosphere. So it's sitting there and just sucking up all that energy, and it radiates it off slower than the land does, right? We have those instantaneous fluxes with the land. You warm up during the day and you absorb all that energy and you radiate it right back off, and at night it's not nearly the repository that water has. And since 70% of the Earth's surface is covered with water, we have the potential to hold a lot of energy, right? So about 90% goes to the Earth's oceans. Another 10% goes into ice and land-based waters, and then just a very small amount gets actually stored in the atmosphere, especially the upper levels of the atmosphere where it's low pressure, I mean, just almost nothing gets stored there. Definitely a good bit of uncertainty associated with these things, because we can't measure that heat flux directly between everything, especially with the heat capacity that water has, and all the various things happening in water. If it was all pure distilled water, that would be one thing, but there's an awful lot going on, like salinity and everything. So there's definitely some uncertainty in this, but we've seen this uh, increase in heat holding, and this is important because we think back to the hydrologic cycle and we think about the fluxes. And if we start thinking about, okay, well, what happens then when we have more energy coming in? Because we do, right? We have more energy being trapped within the atmosphere because of the increase in greenhouse gases. So it's not more from the sun, it's more from the emitted thermal radiation that gets stuck in the atmosphere. So yeah, I mean, 1 billion cubic kilometers of water is sitting in the ocean. A very small part of it is sitting in the atmosphere. Evaporation obviously is the largest movement of water every single year, about 400,000 cubic kilometers, which then precipitates back to, about 40. Well, most of it comes back on the ocean, right? Only about 40,000 kilometers are transported over to land, which is key. This is where we get all of our vegetation and productivity and everything, is these areas that are the deposits of evaporated ocean water. And then over land, water precipitates, combines with surface water and groundwater and everything, and recycled water, and it's about 70 total that get evaporated and transpired back up into the atmosphere. So when you think about, okay, well, what happens if you have more of this ocean of evaporation, which means more of this land precipitation, right? Overall, you're going to get more ocean precipitation as well, but more land precipitation. What does that start to do? Well, the ocean precipitation affects salinity. We're going to talk more about that next lecture. Increased land precipitation, well, it's not evenly distributed, right? So the wet places are going to get wetter and the dry places are going to get drier. But the net effect actually is that since we have no shortage of water here, and we know that the thermal energy to melt ice is less than the thermal energy to vaporize it, right? We basically have this unlimited source of water. So it would reason then, if we know this tie between hydrologic cycle and heat and energy causing evapotranspiration, that we would see an increase in water vapor in the atmosphere. And we do, right? We do. It's variable. It's not nearly as tight and neat as temperature records and CO2 and all that kind of stuff. But it's pretty undeniably a statistically significant trend globally. And it's actually really statistically significant for some parts of the world. And this is really important, right? Nothing is averaged over across the entire, nothing on an individual basis matters when you look at the whole atmosphere. But when you start to think about the significant trends in movement of water vapor in geographical contexts, you start to understand, okay, certain areas are going to be hit or are being hit by the changes in the hydrologic and atmospheric cycles than others. You can't help but notice. So the gray hatching or gray little dots here mean it's statistically significant, and browns mean loss, right? Blues mean gain. And so you can see, right, the stuff that really affects us, we don't have as much happening right now. And we'll talk a lot about that when we get into the ocean. But you look out over here and you start thinking about where the winds are moving and how much more precipitation is, or how much more water vapor is being moved up into the atmosphere here and here and here, especially, you start to understand then the areas and impacted more strongly, at least on the precipitation side, um, under changes in the climate. So hopefully that's a good basics of the atmospheric circulations and hydrologic circulation as it's related to the atmospheric circulations. We'll get into the ocean currents and ocean circulations in the next lecture. Talk about why these places are not increasing the amount of precipitation moving or water vapor moving, and why these are increasing.